Question 16. Apply the relationship between a force F and the work done on a system by the force when the system undergoes a displacement. D. Work equals to F d cosine theta, where theta is the angle between the direction of the force and the direction of the displacement. Mentioned example problem 1 and example problem 2. Number 2. Apply the work-energy theorem to relate the net work done on a system and the resulting change in kinetic energy. Now for 2, we need to mention this part from the study. Now we have something called the work-energy theorem. And it states that the work done on a system equals to the change in the system's energy. So for example, here, if this person does 500 joules of work on the box will gain 500 joules of kinetic energy. So the work done by the person or by the force equals to the change or to the gain of the kinetic energy of the box. So the work is equal to the change in the kinetic energy of the box or any type of energy to be like in general. Work is, or W is the work done in the system, or on the system to be more exact. Delta E is the change in the system's energy. Now remember, whenever we have this symbol delta, that means we have a final value minus an initial value. So the final energy of the box minus the initial energy of the box gives you the amount of change in the energy of the box. For example, the gain of the energy. If the energy gained by the system was kinetic, then the work done by the force on an object is equal to the change in its kinetic energy. So this is حالة خاصة from this one. This one is حالة خاصة from this one. This one is very generic. But this one is when the work done on the system causes a change in its kinetic energy. Now remember, change in the kinetic energy, that means a final minus an initial. Final kinetic energy can be found by half mass v squared, but which v? Well, the final velocity. Since we're finding the final kinetic energy of the object, الطاقة الحركية النهائية للجسم, we substitute the final velocity. نعوض السرعة النهائية. ناقص or minus the kinetic energy or the initial kinetic energy, that's half mass v squared, but which velocity? Obviously the initial. Since we're finding the initial kinetic energy, لأننا عم نوجد الطاقة الحركية الابتدائية بنعوض السرعة الابتدائية. And that gives you the work kinetic energy theorem that we said that you have to memorize. The work done on the box is equal to the change in the kinetic energy of the box, which is 500 here, which is equal to half mass v final squared minus half mass v initial squared. If the question says that this box, this system starts from rest, starts moving from rest, starts moving from rest, that means that the initial velocity is 0, and you get rid of this one because 0 multiplied by the mass is 0, and you're left with only work equals to half mass v squared. Sometimes a question requires you to find the work in branch A by multiplying FD cosine theta, and in B he requires you to find the final velocity زي ما جبت لكم في الامتحان. طيب, let's solve some questions. Example problem 1. A hockey player uses a stick to apply a constant 4.5 Newton force. So this is the force, obviously, forward to a 105-gram puck. So here he gave me the mass for some reason. Maybe we need it, maybe we don't. Let's see. Sliding on an ice over a displacement of 0.15 meters. So this is the displacement, D. How much work is done, or how much work does the stick do on the puck? Assume friction is negligible. So if friction is negligible, that means that there's no friction. The work done by the stick is equal to the force applied by the stick multiplied by the displacement traveled by the puck, cosine the angle between them. Now, this is the puck. You apply a force like this, and surprisingly, it moves in the same direction. Wow. Okay, so the angle between them is 0. There's no angle between them. They're in the same direction. The force, oh, whoops, what did I do? Okay. Oh my God, okay. Okay, let's continue. So FD cosine theta, equals to the force applied is 4.5 newtons. The distance traveled is 0.15 meters. See here the units are okay. يعني ما مش بحاجة لتحويل الفورس بالنيوتن والديستانس بالمتر. Other than that, if the distance is in centimeter, لا سمح الله تضطر تحولي عن طريق القسم على 100. Okay, so be careful about that. Okay, girls, like the conversion is something that we've taken in term 1, so you should be careful about the units. All right, times cosine the angle. We said that the angle between them is 0. Using the calculator, 5.15 times cosine 0. That gives you 0.675. 0.675 joules. Example problem 2. A sailor pulls a boat a distance of 30 meters. So this is the distance or displacement along the dock using a rope. So this sailor pulls the boat using a rope. عم نسحب قارب عن استخدام حبل، وهذا الحبل يصنع زاوية مقدارها 25 درجة مع الأفق. This is theta, the angle. How much work does the rope do on the boat if the tension is 255 newtons? So this is the force. He wants me to find the work. How much is the work done by the rope? So the work done by the rope is equal to the tension force in the rope multiplied by the distance traveled by the boat cosine the angle between them. Now this is the tension force. It makes an angle of 25 with the horizontal. And the boat is not moving with the direction of the force, it's moving forward. So this is the displacement. So you can see that this is the angle between F and D, 25 degrees. The force is 255. The distance is 30 meters. Cosine, the angle between them is 25. Use the calculator quickly. 255 times 30 times cosine 25, close bracket, 23,000. Oh, one minute. What am I doing here? So 255 times 30, like this, yes. 6,933. So 6,933 point something, 0.25, 0.2, let's say just 0.2 joules or 0.3 joules. So this is the work done by the tension in the rope. 25 kilogram skater moves at 2.5 meters per second. So this is the velocity of the skater and stops over a distance of 24 meters. That means that this is its initial velocity. It was moving at 22.5 and then eventually stopped. يعني في النهاية توقفت. So this is its final velocity. It is 0. Ooh, okay. Over a distance of 24 meters. So this is the distance that she covered while decelerating. Find the skater's initial kinetic energy. So he wants me to find the kinetic energy at the beginning, before she decelerates. How much of her kinetic energy is transformed into other types of energy or in other forms of energy by friction as she stops, and how much work must she do to speed up to 2.5 meters again? Right, let's find first the initial kinetic energy. That's half mass initial velocity squared. Half the mass. Oh, where's the mass? Oh, there's the mass. Sorry, I did not see it. 52 kilogram skater. So we have the mass, 52. And the initial velocity, 2.5 squared. Calculator, please. Oh my God. Half 52 and 2.5 squared. 2.5 squared. That gives you 162.5. So this person had 162.5 joules of kinetic energy before she stopped, before she started to slow down and stop. طيب بحكي لي the second question, how much of her kinetic energy is transformed into other forms of energy by friction as she stopped? Now this energy, when she decelerates, when she presses on the brakes of her skates, friction will work, and this kinetic energy will turn into other types of energy by friction, which is heat energy. So 162 joules of kinetic energy will turn into 162.5 joules of heat energy. يعني هاي 162 ونص جول من الطاقة الحركية تتحول ل 162 ونص جول من الطاقة الحرارية بفعل الاحتكاك due to friction. تمام. How much work must she do to speed up to 2.5 meters again? Well, This is another question. The initial velocity unit is 0. The final velocity is 2.5. He wants me to find how much is the work needed to accelerate again from 0 to 2.5 meters per second. Like that uses the work energy theorem. Half mass V final squared minus half mass V initial squared. He wants me to find the work given the initial and final velocities. Well, we need to use the work energy theorem. The work equals to half. Now the mass of this person is 52. The final velocity is 2.5 squared minus half. Another mass, excuse my handwriting, 52 times the initial velocity 0 squared. So let's see how much work she needs to do in order to accelerate again to her initial speed of 2.5. I can't, oh, I can, okay. 0.5 times 52 times 2.5 squared. This one obviously is 0 because we multiply by 0 here. So there's no need to put it on the calculator. So obviously I need 162.5 joules of work. Remember, the work needed to change the kinetic energy of the object is equal to the change in its kinetic energy. So it's just the same. Right, okay, let's move on. This is a question I got you. Yeah? Okay. Diego pulls a sled across level snow. If the sled moves a distance of 65.3 meters, how much work does Diego do on a sled? Well, we can see that in the image, we also have some other info. Yes, I have the distance here, but I also have the mass, I have the force, I have the angle between the displacement vector. Of course, it's going to move like this, and the force. So I have other info mentioned on the image. If I want to find the work done by Diego, I need to multiply his force times the distance traveled by the sled times cosine the angle between them. The force applied by Diego is 255. The distance traveled by the sled is 65.3. The angle between them is 35, just like the boat example. Using the calculator, 255 times 65.3 times cosine 35, that gives you 13,640. 13,640 point something, 0.1. All right, no problem, 0.1. 0.1 joules. 13,000. Okay, now in figure B, if the sled started moving from rest, that means that the initial velocity is 0, started moving from rest. So started initial from rest. That means initial velocity is 0. What is the final velocity? He wants me to find the final velocity. We are going to use, oh, you guessed it, the work kinetic energy theorem, minus half mass v initial squared. Now remember, it said it started from rest, the initial velocity is 0. So ريحني من هذا الطرف, see, because initial velocity is 0. If you multiply 0 times whatever, gives you 0. So there's no need to put that one. Understand? Please don't let me explain this. Okay. Now the work we have found in A to be 13,640.1 joules equals to half the mass 4.5 mentioned in the image, right? Let me just check. Yeah, 4.5 times the final velocity squared. Don't forget the square, please. Now on the calculator, you're going to put the equation and solve for the final. 13,640.1 equals half. Can just write half as 0.5, but whatever. Okay. 4.5 times the final velocity, which is the unknown, so I'm going to put it as x, but I will not forget the square. Then shift calc and equal 77.8. Oh, so the final velocity is a whopping 77.8 0.8 meters per second. Of course, this is a hypothetical question. Regardless, okay. This is gonna take a bit a long time, so I'm gonna do it on a separate video. I don't know. Okay, let's just mention the idea of each question. Here we have a mass of 400. We have the initial velocity, the final velocity. How much work is done? He wants me to find the work. So obviously work equals half mass v final squared minus half mass v initial squared. And then substitute half times 400 times v final 20 squared minus half mass 400 times V initial 10 squared, and then find the answer. Okay, how quick was that? A ball of mass 4 kilogram is dropped from the top of a tall building if the ball falls through the vertical distance of 50 meters. What is the work done by gravity on the ball? Now, this is the force of gravity, okay, and this is the distance. So obviously they're in the same direction. The angle between them is 0. The work equals to FD cosine theta equals the force of gravity. Oh, I don't have the force of gravity. How can I find it? Well, obviously I have a mass. So if I want to find the force of gravity, see, I want the work done by gravity, I need to find the force of gravity. I need to multiply m times g. The mass is 4. G is 9.8. 4 times 9.8. 4 times 9.8 equals to 39.2. 39.2 newtons. So 39.2 newtons. The distance is 50. Cosine the angle between them 0. Oops, that's so close. Okay. And then I use a calculator again. 39.8.2 times 50 times cosine 0. 1960. All right. Well, okay, well, the closest one is this one. Yeah, I think they have 1960 is very close to 2000, okay? I think the difference is just because he said assume that G is 10, where we substituted G 9.8. Oh, it doesn't matter. So very close. Okay. All right, it's taking too long. All right. Okay. Okay, here are some other questions for you to look at. Already solved them. They're all the same idea. Just need to look at them. So you have these. You can pause, you can pause the video and see if you can solve them yourself. You have these. And you have these. The ministry question one is very important. They all follow the same steps. But the difference between the ministry question here and the question that I gave you in the exam is that my question is 2 branches, while the ministry question is just 1 branch. But you still have to follow the same process. You have to find the work first, and then use the work kinetic energy theory to find the final velocity.